Are you able to see the screen? Are you able to see my screen?
Yes, sir.
Okay, okay. So these things then therefore I am not going through. I think you would understand this because you have learned this. What is the generator action? Then just roughly I am touching and going away. So there are slip rings, and here you have two magnets. Within this magnetic field, your coil is rotating. So when it is in the perpendicular position, it will be cutting maximum flux linkage on the coil. So and when it is in the horizontal position, then negligible. So if you differentiate, then you get your EMF equation like this. Okay, so this is how things are explained in any standard book. You will be able to understand if you read through. So mainly is based on Lenz law. So there you see, if we keep E equal to n d phi dt, then or d psi dt. So here it is n remains the same, phi just changes with the angular velocity. So as it is rotating with a constant angular velocity, omega. So based on that, your phi will be maximum when it is theta equal to 0, and minimum when it is theta equal to 90. So based on that, we get the equation like this. I'll just get back in no time. Just wait for 1 second. Okay. So this is how you get your EMF equation, and uh, all those things calculations you can get from here, because EM maximum will be based on n into phi into omega, as we can see it here. So omega we can write as 2 pi f. For our AC supplied frequency will be 50. So we can straight away we can write it as 314 right here. And n is the number of coil in the armature, and B is the maximum flux density, A is your area of cross section. So based on this you get your EM maximum value. Okay, so you can see that if you increase the strength of if it's a permanent magnet, then BM remains constant, A will also remain constant. But if you are using electromagnet, then definitely your BM can be improved before it reaches saturation. Okay. Similarly, the equation of the alternating current will be same as EMF, as we can see from here. And coil circuit has been closed with a resistive load, then only you will get like this. Otherwise there will be a phase difference. So if instead of resistance there is one inductance or capacitance, or pure inductance capacitance, then there will be phase lag for the inductive circuit, lead for the capacitive circuit. But if it is purely resistive circuit, then your current will be in phase with your voltage. So this is what we get. And since omega equal to 2 pi f, where f is the frequency of the rotation of the coil, which is 50 hertz for our case, so then you can write your E as like this. So you can write here instead of omega t 2 pi ft, and then also you can write 2 pi by t, where t is your time period. So t is the time period of the alternating voltage or current, which is equal to 1 by frequency. So here graphically we want to represent, so we can, it is seen that the induced EMF varies as sine function of the time angle omega t. Time angle means omega frequency multiplied with time. When EMF is plotted against time, a curve known as sinusoidal EMF as shown as given in the 6.3. So if we can think like this, your EM is maximum value EM is this of radius, like here if I name it as O A dash, then from there if we take the vertical component of this, then we'll able to find out your entire sinusoid. So these things I would ask you to go through. I'll upload the PPT, so you can go through it and you will get it in any book. Okay. So this is your vector length. It will be useful later when we'll draw the phasor diagram, and that time I'll discuss. Okay. So now we have not only always pure sinusoidal waveform, we also get the waveform which are part of with harmonics. So whenever there will be presence of harmonics in the signal, then you won't get the pure shape of sinusoid. So shape of the curves are obtained by plotting instantaneous values of voltage or current as the ordinate against time as abscissa. It is called the waveform. Okay, but practically it is difficult for us to draw it from the uh, mm, uh, like your abscissa versus ordinate in that way. Only if we use a CRO or a DSO or oscilloscope, then only we'll able to do it. Sine wave is an ideal form and it is accepted as standard wave to the designer, or designer means those who are designing AC equipments for them. The waves, based on that, they do all those sorts of calculation with the assumption that the supply is your perfectly sinusoidal. The waves deviating from the sine wave are termed as distorted wave, which contains harmonic. So the more it is part of, the more harmonic content will be present there. So in that sense, we can anyone can tell that whether Fourier series is taught in this semester in maths.
No, sir.
Okay, okay. So when in future in mathematics you will learn Fourier series analysis, you will see that you can get any odd function or even function in the summation of a DC component and the summation of odd and even harmonics. So whenever there is a odd function, we'll get the odd harmonics, and when it is a even function, then we'll get even harmonics in that way. So you can add even though if you have a step input like this step response, or you get a DC value like this, you can get it in terms of sinusoid, like this is your fundamental, then you have your third harmonic, then fifth harmonic. Okay, so if you just keep on adding this, then you will get, if you just take the summation of all this, you will get some ripple over there, but you will be able to construct the same pulse as it is shown here. Okay, so the more it is distorted from the sinusoidal, the more number of harmonics will be present. So whatever we can see here, we can represent in terms of n number of odd and even harmonics. So we can go till as many as possible, but once we get that the magnitude of that, I mean amplitude of that harmonic signals will be less, those things we can ignore. Okay. And one more thing to mention, that your uh, mm, okay, what I was trying to say, uh, huh. So whenever we do it theoretically, then there will get some function where we get both odd and even. But usually for the our AC supply, whatever is there present, whatever we are getting, there will get some harmonic content because of the nonlinear load. So what is nonlinear load? We may have many electronic devices which are operating at a high voltage. So those are called power electronics devices. So because of their presence, there'll be your the fundamental thing will be distorted, because we are directly not getting from the generating station, so it will pass through the distribution section, transmission distribution, then only we are getting it. So because of the presence of some power electronic devices, we may not always get the, we usually do not get purely sinusoid, there will be always some harmonic present. So when the designer design any equipment, they assume it that the supply will be purely sinusoid. But whenever pure sinusoids are not present, there will be harmonics present, then there will be more heating effects, so losses will be more. Okay. So these can be referred as complex waveform. Complex waves are those which depart from the or deviate from the ideal sinusoidal form. The complex wave having equal positive and negative half cycle can be made up of a number of sine waves with different frequency. These are called harmonics, what I told. The fundamental fundamental harmonic is the harmonics which is having the lowest frequency. Okay. There may be the presence of subharmonic also. I'm not going into that because you won't be getting it here. The waves of higher frequencies than the lowest one are called the harmonics. Like if the fundamental is 50 hertz, for our case it is 50 hertz. So third harmonic will be then 150, fifth harmonic 250 in that way. Okay, the frequency will uh, changes. It's going high at a multiple of 3, 5. Okay. The waves of higher frequency are called harmonic, and as I told, already it is discussed. Complex wave can be composed of fundamental wave and any number of other harmonics with proper amplitude. So here one complex waveform is shown. This is one complex waveform 6.A. So here we can see we have a fundamental harmonic and we have a third harmonic. So you can see that it is more looking like a pulse signal or square wave signal. So if we can include fifth, then it will be even this part will be compensated. So fifth harmonic means this part will go high. So you will get a response like this. Okay. So if you go for 7, then even more. So these things happen. And here also we can see here is a fundamental harmonic. Then we have a second harmonic and third harmonic. So you get a signal which is more common like this. A ramp signal with a negative slope. So whatever signal, whatever function you are having, odd function or even function, you can have it. We can represent them as a summation of n number of odd and even harmonics. And also, if required, there may be some DC offset value. So this is how you can do all this harmonic analysis, and that can be done with the Fourier series analysis. You will learn later in maths. So here we can see that if we have a level bias in the if it is not starting from the 0, it's starting from some 5. So this is your 5 DC. If it is a current, then it is a 5 ampere DC current. On top of that, this AC waveform is there. Okay. Then definition of cycle, that these are also, I think it is known to you. One complete set of positive and negative values of alternating quantity is known as cycle. Or if you start from a particular phase, after one complete cycle, when you uh, uh, achieve, when you arrive at the same phase, the time required is known as the time period, or we are supposed to have a complete cycle, and the time required to complete one complete cycle, to achieve one complete cycle, is known as the time period. So for our supply, AC supply, we have a 50 hertz alternating current, means it is having a time period of 1 by 50 second, which is 20 millisecond. Okay. Frequency is the number of cycle per second, or in 1 second how many complete cycle can be completed by a signal is known as frequency. So frequency unit is hertz, that you know, and F equal to Pn by 120. So P is your number of poles and N is the revolution in RPM. So if it is a two pole machine, then F is equal to 50. If it is a two pole machine, F is equal to 50, then N will be 120 by 2. So 60 we can write. So it is 50 into 30. So 50 into 60 equal to 3 RPM, 3000 RPM. And when it is 4 pole, it will be 1500 RPM. When it will be 8 pole, then accordingly it will change. So 750. So RPM will be changing based on the number of pole. So depends. It is like the relation between the electrical and the mechanical angle. So that also we can write like if it is, if for the concept comes like this, your 360 by P, and there it is. Okay, it is based on three phase, so we should not discuss it here. Later we'll discuss. Anyway, leave it. So whenever we have P number of pole, then N is the revolution in RPM. Then if we get with this relation. So how we are achieving it, we'll discuss later. It may be noted that the frequency is given by the reciprocal of the time period. So it is simple like that. And when you have the frequency in terms of 1 by time period, this is hertz, but we can also write frequency like omega, which is equal to 2 pi f. So there we have to multiply that 1 by t into 2 pi, and then that is having a unit of radian per second. So whenever we write Em sine omega t, that omega is in radian per second. So when we'll be solving using or in the AC circuit analysis, when we'll solve the AC circuit, we'll be using omega equal to 314 for the 50 hertz supply, because this is 50, this is 2, so 100 and 3.14. So 314 radian per second. So whenever we'll see later that reactance will get for the inductance, it will be omega into L. Okay, so those things will come later. Amplitude is the maximum value, whether it is in positive half cycle and the negative half cycle, is called the amplitude. So there is a maximum value we can have it, and we'll see later that RMS value is 1 by root 2 times of the average value. Sorry, RMS value is equal to 1 by root 2 times of the maximum value. Okay, so what is phase? Phase of an alternating current is the uh, fraction of the time period of that alternating current or waveform that has elapsed current since the current or the waveform last passed through the zero position of the reference. So from this zero position, any point here, here or there, it is called the phase, and that either we can represent as a fraction of the time, or we can represent in terms of angle. So we need to just multiply with the omega, which is your frequency in radian per second, then only we'll get the angle. So at this point, it is half of the or 1/4 of the total time period. So based on that, we can say that it is having a phase at 90. So accordingly, we'll get pi, 3 pi by 2, 2 pi. So this is if we have a coil like this, A and B, it's wound over one another, then they are in phase. So there is no phase difference. But if we get a coil like this, C somewhere here, so C will reach the maximum value earlier than A. If the angle between them is equal to delta, then you will having a C waveform which will look like this. So it will cross zero earlier than A and B. So this angle is known as your delta. So this is your phase difference. It is shown in the next slide. So we have three coil A, B and C. If we take A as our reference coil, after that B is lagged by mechanical angle of beta, and then this is a mechanical angle of alpha. So when we have the two pole machine, this is drawn for the two pole machine. So there is north pole, south pole in that way. So then mechanical angle will be electrical angle. Okay. So there is one relation, theta mechanical is equal to it is P into theta electrical. So whenever we are having two pole, then theta mechanical is equal to theta electrical. But when we have four pole, then of course it will be less. So your this mechanical angle will be less than the electrical angle. So here we can see that if A is our fundamental one, then B and C coils are lagging by beta and alpha angle. So they'll be achieving their peak after beta angle. So if radian is given, then beta by omega. So 314, if we divide beta by 314, that will give you the fraction of the time period. So this will give you the fraction of the total time period, uh, that phase difference. So it will take that much of time to reach the peak. And similarly for the C, if we what is the difference between A and C? Mechanical angle is alpha plus beta. So it will take alpha plus beta divided by omega time to reach the peak. So it will be delayed. So C waveform is lagging, B is lagging, but compared to C, A and B are leading. Compared to B, only A is leading, C is lagging, and so on. So we can also represent them in terms of phasors. So then it will be easier for us to deal with when we'll start analyzing the circuit. Okay, so phase difference you can a leading alternating quantity is the one which reaches its maximum or zero value earlier as compared to the other quantity. So this is a leading one. Similarly, lagging is the other way around. So here the example I have already discussed. So three equation we can write like this. A is leading compared to B and C. So we should write omega t minus beta, and C we should write as sine omega t minus alpha plus beta. Okay, so if we take B as our reference, if we write this as reference, then it will be Em sine omega t. Then this will Em omega t plus beta, and this will be omega t minus alpha. Okay, so this is how you should represent when there is a delay. Now let us come to the RMS calculation. What is the concept of the RMS value? So in case of AC fundamentals, we should get the effectiveness of the current, effective current or effective voltage we can calculate based on the power consumption or the heating effect. Okay, so we, how do we compare? We have two circuit and we have one wattmeter. So what we do, we have a first we have the AC source, and for that through a resistor we connect to resistor, and we are trying to have the heating effect of the resistor, which is equal to zero point 0.4 0.24 I square RT, where R is the resistance, I is the current through it, time taken by it. So if we divide by time, then we'll get the power consumption through the wattmeter. Okay. So now to have the same same power consumption, we just replace it and we add a variable DC supply, and we just note down the current which is flowing through it, which will generate the same wattmeter reading as of the AC source. So that will give you the RMS value. That DC value here will give you the effective RMS value for the AC supply. Okay. So how can we find it out? So here it is equal to I DC square RT and 0.24. And here, how can you write it? It is 0.24 into integrate. You have to integrate it from 0 to 2 pi, and then you should write Im sine omega t and all those things. And then once you solve this analytically, you will get your RMS value. So it is done later. We'll come to that. Before that, before the analytical method, it is shown there is one more method which is called mid-ordinate method, and it is useful for the waveform with harmonics. So whenever we get a complex waveform, we can just split the entire time period in terms of n number of small segment, and for that we take the average value. And once we take the average value for it, then we can write the heat produced in the first interval. It's like this, that much of kilocalorie. then the second interval, then nth intervals like this. So once you add them up, you get this as your effective heating effect, and then that will be equal to IDC square. So IDC will be equal to root over of uh, this RMS value. I mean, this is your RMS value because it is root of mean of 1 by n is the mean of the square. So that is how we can get, which is called mid-ordinate method. Same thing is applied for the voltage because I square RT we can write as V square by R. So in that way also we can get the same, we can arrive at the same point, same relation. Analytical method is what? Integrating it. So what we do, we just take the square root of this because already we have seen we are arriving here. Instead of adding them, we are just integrating here from 0 to 2 pi for the one time, for one complete cycle, 0 to 2 pi I square into d theta divided by 2 pi, because we need to average it like this. Hence the RMS value we can calculate like this. We can take 2 pi out and sine square Im square we can take out because that is constant. I equal to Im sine theta. We are just writing theta omega t as theta. If you wish to, if you can integrate with 0 to t sine square omega t in that way. Okay, dt. So that is also acceptable. So then you can replace sine square theta by 1 minus cos 2 theta by 2. And then if you solve it, if you now operate the limit, integrate and operate the limit, then you will get that I comes out to be this. So this you should always remember. And why do we do this? Because all our the effect power consumption will be in terms of RMS value only, and your meters will be reading in terms of RMS value. So RMS value of the current is 0.707 into that of maximum value. Only thing, peak value will be required when we deal with the capacitive circuit, because there the maximum voltage matters. Okay, so uh, average heating effect produced in one cycle I square R is equal to Im by root 2 square R. So half Im square R is equal to your average heating effect when we express it in terms of maximum Im peak value. So if you have a complex wave with your harmonics, here we can see that our fundamental frequency is omega. Then we are having 3 omega t, 5 omega t, and that is also have some phase difference. So whenever we get such expression, then we can find out the RMS values like this. So you can take the peak value of each sinusoidal component and then take 1 by root 2 of that, so that square, then you uh, uh, have your effective heating effect. Okay, so you get the root over of all. If you take the square of this and then you take the root over of this, you will get your total current. And if there is a DC current, DC component of 5 ampere in addition to this, like plus 5 here, then that can be added like 5 square without using 1 by root 2. So this is how you get your RMS value for the complex waveform. Now let us come to the average value. So average value of an alternating waveform or current is expressed by the steady state current which transfer across any circuit the same charge as transferred by the alternating current during the same time. Okay, so average value of a symmetrical alternating current is that is one whose two half cycles are exactly similar, whether sinusoidal or non-sinusoidal. Then over a complete cycle it is zero, and it is well understood because if it is triangular also, then this area is plus and it's minus. If they're same, then average thing is zero. Hence the average value of a symmetrical alternating current obtained by adding uh, or integrating the instantaneous values of the current over one half cycle only, we follow that part, because if we do it for the complete cycle instead of half cycle, we'll get 0. So what we do, we take t by 2 and we integrate from 0 to t by 2 or 0 to pi if you are willing to solve with the angular approach like omega t. Average value of the unsymmetrical alternating current, that is one whose two half cycles are not similar, like half cycles of a it's a halfway rectifier or full wave rectifier, then uh, it can be obtained by add or integrating for the entire whole cycle. Okay. Or when we have a half wave rectifier like this and this, then also we should take the complete cycle, not t by 2. Only thing is when it is a uh, 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 when it is having a two exactly similar cycle, then which are having a different polarity, then only we'll get it. Otherwise, we'll not do it. So here we should take 0 to 2 pi only, or 0 to t. Okay, so here also we can take the mid-ordinate method or analytical method. So mid-ordinate is same like your entire time period. You segment it by n number of segment, and then you take the average of this, and then you will get your average thing. And if you want to do it analytically, then if it is a standard alternating current which is having the exact sinusoidal thing, so 0 to 2 pi, will now take only for pi because it is a exact similar negative half cycle. So we take the average from 0 to pi and then I dt. Okay, I is equal to Im sine theta. So Im we can take out, and then if you integrate, you are getting this. So 2 Im by pi or Im by pi by 2. So it is twice the maximum current divided by pi. So now you can find out I average by I average equal to this. Yeah, because you know pi is equal to 3.14, so 0.637 of the maximum value, and from there you can get form factor. Form factor is the ratio of the RMS value by average value. For sinusoidal alternating current only it is 1.1, but for the non-sinusoidal it will vary, and in case of sinusoidal alternating voltage also it will be same, because instead of Im only there will be Em. The knowledge of form factor is used to find out RMS value when we have the concept of average value, and other way around when the other is known to us. Okay. Crest or peak or amplitude factor is simple. It is maximum value divided by RMS value, which is root 2, 1.414. Okay, so this is crest factor, and that is also holds that magnitude holds only for the sinusoidal. So this factor is used to find out, as I told, the dielectric stress of the insulation, because when there is a insulation means there will be some capacitance formed, and that is proportional to the peak value. So even though the RMS value, for RMS value it is not discharging, but because of this peak it can discharge at that particular instant where the peak will be achieved. So that's why we have to mind the peak term. So whenever we calculate something, and then for a dielectric circuit, direct to be used in circuit, when we calculate a voltage, we should multiply with root 2 and check whether it is allowing its limit or not. So this is the root mean square value for the half wave rectified alternating current. So here the negative half wave means this negative cycle won't be present, but we should integrate from 0 to I mean when we divide it, we should divide with 2 pi. So we integrate from 0 to pi, then pi to 2 pi will be anyway 0. So we can write 0 to pi I square dt, and that we should divide not by pi but by 2 pi. So if you solve this, then your RMS value will turns out to be zero point 0.5 into Im, or Im by 2. And the average value is same, we should divide by 2 pi, and it's like that. It will be now, instead of 2m by 2Im by pi, it is now Im by pi. So in that case your form factor changes, you see, your form factor is 1.57 and crest factor is 2 instead of 1.414. So those kind of problem you can expect in your continuous assessment 2. So practice well this kind of problem instead of concentrating more on the theoretical part. So here is one example. Here we can see that we have a waveform like this with a time period of 8 seconds. We have to find out the RMS values. Then how can we calculate it? This is 10 for 2 seconds. So 2 into 10 square plus minus 4 into uh, minus 4 square into 2 again, then again 2 square into 2, then 0 into 2, that divided by 8. And if you take the root of this, then you get your overall RMS value. So here it is very simple, but if there is a instead of square, if it is rectangular, then what will happen? If it is a ramp, sorry, not rectangular, if it is a ramp, then what will happen if you get things like this, and then you get like this. So if you get that kind of response, then you should get the function first, and you should get first the expression of it. So if we take this as your x, and or if you write this in terms of t and this in terms of y, then what is the slope? It is from so y by t is equal to here what is your slope? 10 maximum is 10 by 2. So y is equal to 5t is your equation. So then if you are finding out RMS, then it will be 25t square, then integrate from 0 to 2. So accordingly it will be 25 t cube by 3, limit from 0 to 2. So in that way you should keep on solving. So there is one more example like this as I was showing here. So time period is given as t. So we should calculate like this, and it is starting from 10. 10 with a slope. What is the slope? If you take the slope somewhere here, it is 20 by 10. So it is 2, right? Oh, sorry, it is not 20. It is 20 here, 10 is here. So 10 by 10. So slope is equal to 1. So we can write it as 10 plus 10 by t into small t. So that if we have to find out the RMS value, this is your expression. So you get the square of it and then you solve. So here it is shown how you calculate it. And then to find out the average value, we just solve it as simple like this. And the RMS value, for that we get this is your mean value, mean square value, and then RMS value will be root of this 700, root over of 700 divided by 3. So it's like this, y squared dt. So you get your this thing, or you can, if you wish to, you can change your scales and all. That is also possible, and with that you solve it like your usual integration. So now representation of alternating quantity, we represent it by this, as we call it phasor. So it is having a magnitude, direction, and the sense. So it is rotating right in the counterclockwise direction. And if we consider a circle like this with a radius is this, now this is your maximum value of the current or voltage, whatever it is, which is EM. So OP is equal to EM. Now it is rotating with the counterclockwise at a angular frequency of omega. Okay. So now if you take the vertical component along this, then you will get the magnitude which is equal to your EM sine omega t. Okay. So as your t in changes, if your t equal to 0, EM will be equal to 0. If t equal to capital T by 2, so you get your EM as maximum, and so on. So this is how, if you draw this is in the complex plane actually. So if you can write this as e power v into that particular angle, v is the thing, and angle is equal to omega t, then or v, not v, actually we can write it as em. So em, and this is your omega t is your theta, then we can write the cosine this point as em cos omega t plus plus j into em sine omega t. So if we take the component along y axis, then imaginary axis, then we get em sine omega t magnitude. So instead of v, just think it v. So e. So em sine omega t will get along the y-axis. Okay. So this is how we can represent a phasor. So the length indicates the peak value of the waveform. And if we have the two, if we have em like this and current is this, or current is somewhere here, which is im, and if this angle is equal to alpha, then we can write im as I as im sine omega t minus alpha, because it is lagging, because of it is a there is a phase lag between the voltage and the current. So this arrow gives the direction. There is a sense with which it is rotating, like if this is rotating counterclockwise, your eye will also rotate, and it will achieve its peak somewhere here after the alpha angle, elliptical angle. So this is how you can represent the phasors. Okay. And actually what happens when we solve, when we calculate, analyze the AC circuit, we represent the phasors in RMS values, not in their peak values. So this is a very common practice, so don't confuse with that. But the idea came with this as your peak, this length as your peak, otherwise you won't be achieving the same thing, same value of your sinusoidal component, sinusoidal waveform. Okay. So these things, I think it is a recapitulation for you. These are all known to you. So from the next class, we'll be going through very quickly this part, the AC fundamentals, and we'll solve a few problem which is there in your uh, midterm. Okay,
Sir,
so
please share the PPT, sir.
I'll upload right now. Only I'll upload. Okay, and you follow the book as I told, whatever books are given, you can follow the same books. Huh?
Okay, sir. Thank you, sir. Have a nice day, sir.
Thank you,
Thank
sir.
you, sir.